Okay, in this video, I'd like to talk about why element 115 had to be cut into triangles and then why those triangles had to have their corners rounded on them. It's all to do with stability and energy flow. So let's get started. Okay, back in 1989, Bob Lazar came out and said the way that Los Alamos was manufacturing element 115, once they got it, was they had discs of it, and they would stack the discs on top of each other until you had a full cylinder of 115. Once you had a full cylinder of 115, they would then take and make a cone out of it. Once you got your cone shape, they would then cut a triangle out of the cone. So once you had your triangle cut out of your cone, they would then slice the triangle and you'd be left with a 3D triangle in which they would then round the corners on it to give you that shape there. Because it's all about trying to get to this right here, this bent pyramid looking triangle with the energy orb around it. Because it's all about the flow. So I wanted to try to figure out what was so specific about this shape. So once again, it's all about the tetrahedron, and the tetrahedron symbolizes harmony and equilibrium. The four corners point equally distant from each of the others. There's no stress or strain or tension in the tetrahedron. Rather, it's at rest or at zero. So that's why it sits here at my 0 point, my event horizon, between matter and antimatter, between space and between counter space, between electromagnetism and visible light and everything that you can see, to dielectricity and pure ether, everything you can't see. This would be the black hole, this would be the white hole, this would be the event horizon. In between, the plane of inertia. Here's your electromagnetism, here's your dielectricity. These two things oppose each other. This is like the neutral ground here. This is the dimensional jumper between space and counter space. So the tetrahedron is the key to all of this, because what you're trying to do is get to this. This is the flower of life, the six-pointed star. Once you round these corners on your triangle, now you're tapping in, because everything's spinning. So in magnetism, invisible light, everything's moving in the matter world. So the shape is called the Rouleau triangle. It's also called a convex circular triangle or a spherical triangle. A convex circular triangle may be constructed by three circles intersecting each other and represent the area of intersection. Its edges are all curved outwards. The sum of the internal angles of a circular triangle is greater than 180 degrees. It's called the Rouleau triangle. It's a curved triangle with constant width. The simplest and best known curve of constant width other than the circle. This is a key, very important. This is what it's saying. It's saying that a circle has the same width in all directions, meaning that if you take two parallel lines or two parallel bars and place them on each side of the circle, no matter what angle you place the bars, it's always going to be touching. So it always has the same constant width. So this is a really key thing to understand in this whole deal. So it's formed from the intersection of three circular discs, each having its center on the boundary of the other two. Constant width means that the separation of every two parallel supporting lines is the same, independent of their orientation. Because its width is constant, the Rouleau triangle is one answer to the question. And here's the question. Other than the circle, what shape can a manhole cover be made so that it can't fall through the hole? The answer is the Rouleau triangle. This is a very big concept because this thing is acting like a gateway or a door to between dimensions. It's called a spherical triangle, but the term more properly refers to triangles on a curved surface of a sphere. The guy who come up with this is Franz Rouleau, and he's a 19th century German engineer who pioneered the study of machines for translating one type of motion to another. Very important. And he uses this in his designs. So other examples of this are Gothic church windows, guitar picks, pool ball rack, fire hydrant, pencil and drill bits for drilling fillet square holes. So, like I said, it wouldn't be the head side of the coin and it wouldn't be the tail side. It would just be the side, the plane of inertia. It's just the event horizon. So, the Rouleau triangle has the minimum area and the sharpest, smallest possible angle at 120 degrees at its corners. By several numerical measures, it is the farthest from being centrally symmetric. It provides the largest constant width shape, avoiding the points of an integer lattice, and is closely related to the shape of the quadrilateral, maximizing the ratio of perimeter to diameter. Here's the key. It can perform a complete rotation within a square, while at all times touching all four sides of the square. So that's what this whole thing is showing you too, in rotation. And it's all about squaring the circle, circling the square, that whole concept. It keeps coming back up from ancient times. So I'll say it again, it can perform a complete rotation within a square while touching at all times all the four sides of the square. So what it's saying is that it has the smallest possible area in this rotational process. It fails to cover a small fraction of the square area near its corners because they're rounded. Because of this property of rotating within a square, the Rouleau triangle is also known as a Rouleau rotor. So this is the key to the energy flow. This is how you're tapping into 0 point. Rouleau triangles can be generalized into 3 dimensions in multiple ways. The Rouleau tetrahedron, which has an intersection of 4 balls whose centers lie on a regular tetrahedron. It doesn't have a constant width, but listen to this. It can be modified by rounding the edges to form the Messier tetrahedron. The Messier tetrahedron, which does. The surface of the revolution of a Rouleau triangle also has a constant width. So when this thing is in revolution, it also has a constant width. Just like the side of this magnet or a coin, it has a constant width. This width is never going to change. So, according to Plato's laws, the circle arcs in 2-dimensional soap bubble clusters meet at 120-degree angles, the same angle found at the corners of a Rouleau triangle. It is possible to construct clusters in which some of the bubble takes on the form of a Rouleau triangle. Then they tell you the shape was first isolated in crystal form in 2014 as a Rouleau triangle disc. Now listen what they made the discs out of. Basic bismuth nitrate discs with the Rouleau triangle shape were formed from the hydrolysis and precipitation of bismuth nitrate in an ethanol water system in the presence of 2,3-bis. So they just made it out of the most anti-magnetic thing that we have readily available on the planet, bismuth. So they're already telling you that they've been experimenting with discs of bismuth, and that's what they're using them for, is this stuff right here. Because it's all about the geometry and how this energy flows. It's all about tapping into that 0 point. So that's how you're able to extract by using this shape. Because it's just like a tap. You're trying to manipulate the energy to be able to control it, to use it somehow. And this is just like controlling a nozzle on a faucet or on a garden hose. It's the same thing. You're trying to make it do what you want it to do. So that's how this whole thing is working, and that's why they had to cut the element 115 into triangles, because of stability and because of the way that the energy flows. So Lazar wasn't lying. He was correct, and that's how this whole thing's working. If you haven't seen my other videos, please check them out. Thanks for watching.